Okay, so I'll take through question one. Got a table of electrode potentials. Most positive one at the bottom of the table, most negative one at the top of the table. Even though it's not a negative number, it's the most negative electrode potential on the table. And the first question is asking us to identify the most powerful reducing agent. So in order to be a reducing agent, we must appreciate that it itself, in order to be a reducing agent, must be oxidized in its own right. So in order to undergo oxidation, it has to lose electrons. And so in terms of an equilibrium, that must have to go to the left-hand side of an equilibrium. So what we're looking for is an equilibrium which exists more on the left-hand side than any of the other equations we're looking at. Electrode potentials, when they're positive, tend to go towards the right-hand side of an equation. Therefore, in order to be the most powerful reducing agent, i.e. be itself oxidized as strongly as possible, we have to have an equation which lies mostly towards the left-hand side. So in order for that to exist, we need to be looking towards the most negative electrode potential. Now, in order to answer the question, though, the most powerful reducing agent is the one which will be oxidized and is the one which will go towards the left-hand side of the equation. So in actual fact, the answer to the question is iron 2 plus, not iron 3 plus. It's the iron 3 plus iron 2 plus couple, but the iron 2 plus is actually the most powerful reducing agent because it itself wants to be oxidized more than anything else in the table. Once you then have that, the next question is actually relatively straightforward because the most powerful oxidizing agent, by essentially the exact reverse of everything else, is usually in a diagonal line across the table. It's the most positive electrode potential and is the species on the left-hand side of the most positive electrode potential. So in this case, it's F2O. And then in order to answer the final part of this question, all of the species which can be oxidized by bromate ion there. Now the bromate ion here, just change colors, don't get confusing. So the bromate ion here, in order to react, okay, so in order to react, this reaction is going to go in the forwards direction. This has a positive 1.52 volts as an electrode potential. Therefore, in order for that to go forwards, it must force in the reverse direction anything which has got a lesser voltage. So that's this one and also the one just underneath it there. These two are too powerful to be able to force backwards. So the only two species which can be oxidized in acidic conditions by the bromate ion are the iron 2 plus again, plus the two the chloride ions in the equation below. Now, when we look then at the next question, which is then the couple between the iron 2 and the bromate ion, so actually this question is taken into here. How do we deduce the EMF of the cell? What we do is we take whatever the cell is on the right-hand side and we subtract from that whatever the equation is on the left-hand side. When we do that, we don't change the values of the voltage. So the right-hand side has a voltage of 1.52. The left-hand side has a voltage of 0.77. The minus sign in that equation changes the sign for you. Don't change the sign of the voltage of the couple and then subtract it. You're counteracting what you've already done. So the EMF of that cell is 1.52 minus 0.77. Okay, so 0.75 as a voltage. The half equation that then occurs at the negative electrode is the left-hand side one. And so the half equation for that is simply Fe2 plus going to Fe3 plus. And in order to do that, the electron has been lost.